Neurons are the functional and fundamental units of the nervous system that convey electrical signals. Neurons normally cannot be replaced and are anatomic, meaning they don't divide, leading them to be some of the longest-lived cells in your body. Within the central nervous system, humans will die with most of the neurons they are born with. In a neuron, there are several main parts that are essential to neuronal functions. The nucleus controls the neuron. The soma, also known as the cell body, keeps the cell functioning and organizes everything inside of it. The cell membrane, which protects the cells. Dendrites, that receive the signals from other neurons. Axons, that transfer signals to other cell organs. The axon hillock, which generates impulses within the neuron. The axon terminals, also called synapse, that forms junctions between the neuron and other cells. Schwann cells that produce the myelin sheath, which is what increases the speed of the signal traveling through the neuron. And finally, the nodes of Ravier, which allow diffusion of the ions. Resting membrane potential is the electrical potential across the membrane of a cell. It is the potential of the cell membrane to move charge and create an electrical current. It comes as a result of different concentrations inside and outside the cell of positively charged sodium ions and negatively charged potassium ions. A typical membrane potential of a neuron at rest and ready to be activated is -70 MV. When the local membrane potential changes, voltage-gated channels, our proteins, react to this change, whereas ligand-gated ion channels, which are large receptors, form membrane ion channels that, once activated, based on the direction of the ion flow, can hyperpolarize or depolarize the membrane potential. These are different forms of passive channels due to them needing to be activated, whereas these are always open and ions can pass through them. The resting membrane potential is maintained by these voltage-gated sodium and potassium channels and the active sodium-potassium pumps, which we will discuss more later. These pumps are active because they are moving against the concentration gradient, which is why it needs ATP for energy due to the extra force required. This concentration gradient is known as diffusion force. This occurs when the concentration of particles is uneven and is higher in one area than another. When this happens, the particles move from an area of higher concentration to an area of lower concentration, meaning across the concentration gradient. This is passive transport. This series of events is what occurs during an action potential.
How does a neuron receive a signal? Other neurons send out neurotransmitters from their synaptic terminals, and these transmitters are received by the dendrites. Dendrites are the tree branch-looking things on the left side of the neuron, as shown here. How is a neuron stimulated? The signals dendrites receive can be classified into excitatory and inhibitory signals, which promote action potentials by increasing stimulation, or decrease the chance of an action potential by decreasing stimulation of the neuron. Also, the proximity of the signal received to the cell body is a large factor of the strength of the stimuli. Neurons can be stimulated but not reach an action potential, which is where the threshold to fire and action potential comes into play. With enough excitatory signals sent to dendrites nearest to the cell body, the neuron will reach a membrane potential of -55 millivolts, causing an action potential to fire. What is an action potential and how does it occur? An action potential is the communication of a signal from one neuron to another. These typically last just 1 millisecond, start to finish, or on this graph that I'm drawing, from point 1 to point 6. First, like I said earlier, the neuron must receive enough excitatory signals to raise the neuron's membrane potential from the typical resting membrane potential of -70 millivolts up to -55 millivolts. Then, the action potential has officially begun. Ava will touch more on what happens with voltage and ligand-gated channels next, but it's important to see how the charge of the neuron fluctuates. Some important locations to note are the threshold of -55 millivolts at point 2, the absolute refractory period at point 4, meaning that it is completely impossible for another action potential to be fired in that instant, no matter the stimuli. Point 5, the hyperpolarization of the action potential, the relative refractory period, and 0.6 when the charge returns to normal.
Action potential moves down the ion due to the influx of sodium depolarizing nearby segments of an axon to threshold. The rising phase is caused by the opening of voltage-gated sodium channels. These ion channels open immediately and are activated once the cell's membrane potential reaches threshold. The electrochemical gradients drive sodium into the cell, causing the depolarization. The following phase of action potential is caused by the inactivation of sodium channels and the opening of potassium channels. This allows potassium to rush out of the cell because of the electrochemical gradients, taking its positive charge out of the cell and repolarizing the membrane potential, which in turn returns the cell's membrane potential back near rest. As the membrane potential returns to the resting level, the sodium channels will deactivate, returning to the closed position. The potassium channels will also close, but they remain open long enough to cause a hyperpolarizing undershoot as potassium continues to move towards its equilibrium potential of negative 70 millivolts. Once the voltage-gated channels close, the sodium-potassium pumps will reestablish the proper ionic concentrations needed for the electrochemical gradients. This action, along with the open leak channels, will return the cell to its resting membrane potential. Action potentials only move in one direction. The refractory period keeps the action potential from moving backwards down the axon. The axon also has myelin sheaths that allow for the sodium ions to flow down the axon through leaky channels, which is called saltatory conduction. As the action potential moves from one node of Ranvier to the next, the inactivated sodium channels in the previous axon segment prevent the membrane from depolarizing again. This is why the action potential can only move forward towards axon segments with closed sodium channels. Understanding action potentials is incredibly important in understanding the functioning of our brain. Our body alone functions on action potentials, or electrical impulses that send signals through neurons and allow us to move our hands, legs, and any part of our body.